Hi guys, welcome to the electricity introduction tutorial. Electricity is part of the electromagnetic force, and electricity comes in two forms. So electricity can be static, which means it's not moving. That's actually what the word static means. It's also where the word stationary comes from, not moving, that kind of stationary, not the kind you write on. And then there's current electricity, which has moving parts to it. And you might be wondering at this point, what's moving in an electric current, or what's happening in a static charge? So let's talk about static electricity first. This is the kind of electricity where we have a charge, but there's no actual moving current. This happens when the material picks up a charge. Two materials pick up a charge. One is positive and one is negative. And this happens because atoms contain charged particles. Some of those particles can move and some can't. So if you remember, we talked briefly about the fact that atoms are made up of these smaller particles, protons, neutrons, and electrons. I'm just drawing 6 of these particles, and I'm going to add little plus signs to 3 of them. Do you remember what the name of the particle is that has a positive charge? It's a proton. So the positively charged particles are protons. And the other ones that I have there are neutral. They're neutrons. They have little ends inside of them. So there you go. That's the neutron. And he has no charge. And then way out in the outer reaches of the atom, way out here, far, far away from the nucleus, that's where we'll find a source of negative charge. And I'm going to draw those as blue little e's. Letter E, letter E, letter E, and they have a negative charge. And there's 3 electrons here because there are 3 protons, and positive and negative charges, you'll remember, are attracted to each other. So the electron is negatively charged, and it's attracted to the proton. It's also repelled by other electrons. So if 2 electrons get near each other, here's one and here's another one, they will actually push apart. They will repel. And if an electron gets near a proton, then it'll be attracted to that proton. So it'll pull that away. Proton is also attracted, but it would be unable to move. And that's because in the nucleus of the atom, these protons are very tightly held by that force we talked about briefly called the strong force. It's pretty hard to overcome the strong force, so protons stay put. But electrons, on the other hand, can be rubbed off very easily just by friction because they are actually pretty far from the nucleus. Some electrons are harder to pull off than others are. It's usually just the outermost electrons that we can sort of peel away by rubbing. And this is why when I rub a balloon in my hair, I usually am trying to get some electrons to rub off from my hair to the balloon. And that's very easy to happen because my hair also has a positively charged nucleus in it. This whole thing is positively charged. So those electrons, if I rub them off, will quickly become attracted to the positive charge in my hair, and they'll sort of hang out there, and they'll stay put on my hair, at least temporarily, and this is what we call a static charge. My hair now has a static charge. Let's look at that on the next page. Okay, take a minute and try and understand this picture that I've drawn. This is supposed to be a single strand of my hair, and this is supposed to be a balloon. And what I'm trying to show you is that there are actually billions of atoms in both of these things, but I've only shown the positive and negative charges, and there would be way more than this. This is just an example. In both materials, the amount of positive and negative charge is actually equal. So for every little plus sign that I have, I should also have an electron with a negative charge nearby somewhere. And that's what I tried to do. I may have not counted exactly, but I meant to. So all of the charge is balanced. So the net effect here is that this is a neutral object. both the balloon and the hair. But if I rub the two things together, then the one that has electrons that are more easily moved will allow electrons to come off, and they will get stuck on the other object. And I'm not really sure exactly which gets the electrons rubbed off, but I'm under the impression that the electrons move from my hair to the balloon. So let's do that. So let's imagine that I've rubbed off this electron right here. And of course that electron now is on the balloon. So he's over here. And I'm going to rub off this electron over here. There we go. He's gone, more or less. Hard to get every little bit of the electron. Oh, took some of my hair with it. And we're going to move that electron over here. And you can kind of get how this is going, right? I'll do just two more real quick. So this electron, and we'll take this electron, and now we'll put those over here. Whoops, wrong pen size, my bad. Gotta go back to the little pen. There we go. Two new electrons. Okay, so now you can see we're no longer neutral, right? So that neutrality is gone because we have actually a buildup of charge in the two locations. So let's get rid of this word neutral and get rid of our arrow. And what we'll do is we'll now label this side has more positive charge on this side. Oops, keep messing up the pen thing. Sorry, guys. It's not easy making a tutorial. Okay, here we go. So on this side over here, you can see there are more positive pink plus signs. So we're going to say that this side now has a positive charge. My hair is positively charged because it's missing some electrons, and so now the positive charge outbalances the negative charge. And on this side, we now have extra electrons, so we have a negatively charged balloon. So what happens when we do this? Well, if we now bring my hair and the balloon close enough together, we'll find that the two things attract, because the positively charged hair will be attracted to the negatively charged balloon, and they'll want to hang out together. And so this is, in theory, an example of an electrostatic charge. Electrostatic charge. Because you'll notice that no electrons are flowing. Yes, they were moved off, but they're not flowing like in a current, which is the other kind of electricity. Current electricity is a little bit different. It still involves electrons though, but this time we have to get the electrons to move along a wire. So I've drawn a wire over here on the right-hand side. So this is our wire. It's made of copper. And I've put some source of positive charge. It's not important right now where that positive charge is coming from, but it's there to pull electrons towards it. So inside of this wire, we've got a bunch of atoms, many more than I could possibly draw. So this is inside that wire. Quick view inside the wire. And it's more than 2 atoms thick, but this is just to give you an idea of what's going to happen inside the wire. When we say that electricity is going to flow through the wire towards the positive charge, what we really mean is that these little itty-bitty electrons that you see, and I'll circle the electrons with a light blue so you can kind of get a look at them. These guys here, these little tiny electrons are all going to be attracted to the positive charge. So we'll put that positive charge in at the bottom here. Make that a little bigger. There we go. Now, the original thought is everybody thinks, oh, all those electrons are just going to line up like in a conga line, right? Like, and do like the bunny hop in a row or something like this. Oop, pardon. Let me undo that. And just get a smaller pen. I think I'd learned from my past mistakes, right? So a lot of people think, oh yeah, they're all just going to get together, you know, and like la 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 la, we're all going to travel this way. And that's sort of what happens. But actually what happens is These electrons that we're showing around these atoms are actually what we call free electrons, meaning, yeah, they belong to the atom that they're with, but they're not that closely attracted to it. And you can even see this, like if you look at this one right here, he's sort of on the boundary between two atoms. So he could actually kind of belong to either one if you really think about it. There's a source of positive charge equidistant from that electron, and where he winds up is really going to depend on the other electrons near him. Because if you think about it, those electrons repel each other, so they try and get away from each other while simultaneously trying to get near a positive charge. So what happens isn't that all these electrons get in this line and go that way. It's that each electron moves to the atom next to it. So this one that I have circled here, this guy, will go this way, and this guy will go this way. And it's sort of like if you imagine a bunch of students all standing in a line, and they're carrying, each student has in their arms a basketball that they're holding. And the student next to them has a basketball that they're holding. And so does the student next to them, holding a basketball. So if this guy here, passes his ball to this guy would have to pass his ball to this guy, and this could go on for a while, right? And this is kind of how electricity moves through a wire. It's not that a single electron travels from its home base of here all the way to here. It's that he moves one atom over, and then the next atom gives up one electron, and so on. So in the end, every single atom still has all the correct number of electrons that it's supposed to have, but a charge is moving through the wire. So this is a current, and you can increase the current by increasing the positive charge, and you can also affect the current by changing the material you're using, because some materials have lots of these free electrons floating around, lots of these guys, and other materials have next to none, which is why some things conduct electricity really well. Like metals are excellent conductors of electricity. But things like plastic and wood, not so much. And this is because the structure of their atoms is such that the electrons aren't really free to be moved around. It's like the basketballs are being held really tightly in those atoms, and they just won't give them away, no matter how much we push and shove. And this is why all wiring in your house or in your appliances is coated with a plastic coating to insulate it. Insulators are materials that electricity does not flow through very easily, and so you don't get a current through them. And you always want to insulate a wire so that the electric current doesn't wind up flowing through you. You're a pretty good conductor of electricity, it turns out, for a lot of complicated reasons. Okay, see you guys in class.